Okay, the class is part 3, second order systems. So part 1 was an introduction to second order systems. Part 2 was about the behavior. Part 3 is going to be about performance metrics. This will be quite short, actually, I think. All right, so performance metrics. Now, you remember from first order systems, we had things like the rise time. Well, second order systems also have their own metrics as well, some of which overlap with first order systems. So what I'm going to do here, I'm going to draw this diagram. Okay. So this is going to be time. And that's going to be the response. And then I'm going to draw I wasn't too good there. Oops. Let's try it again. So I'm going to draw a damped oscillation. Okay, there you go. Now this is oscillating around a steady state. Oops, what happened? Around a steady state, here we go. So that steady state is probably about there, okay? So this damped oscillation is slowly approaching that steady state, right? So what's happened here, time 0, we impose a unit step, and then the system responds, okay? And this is what we see. Now, there are a whole bunch of metrics you can talk about for a second order system. We still have the rise time, right? So let's talk about the rise time first. We still have the rise time, which is TR, but it depends on whether you're talking about the damped oscillation when zeta is less than 1, or a damped system when zeta is greater than 1. If zeta is greater than 1, the rise time is similar to the first order one, which is time taken to go from 10% to 90% of the steady state, okay? Now that's okay when you have, some kind of monotonic thing like that. You just measure the time, say at 10%, and measure the time at 90%, right? That's the 90%. That's the 90% across here, and that's the 10% across there. For oscillation, it's not so easy. It's not so obvious what you would do. So, this is when. So in this case here is when zeta is greater than 1. Okay. All right, that's greater than 1. If zeta is less than 1, right, then the thing will show damped oscillations. And what they then talk about is the rise time is basically how long it takes for the system to go from the starting point to the first place it crosses the steady state axis. Okay, so that's the rise time. All right. So if you've got a damped oscillation, your zeta is less than 1, the rise time is defined as the time it takes to go from the starting point all the way up to the first crossing point, the first time it crosses the steady state, okay? So this is the rise time across there, right? All right. Now, I'm not going to give you the formula here for these. You can find that in the textbook, but there are various formulas for computing all of these. Now, and the formula for the rise time for the case when zeta is less than 1 is different from the formula for when it's greater than 1. Okay, that's the only thing one has to be aware of. The other one is we still have a settling time. So we had a settling time for the first order one, and you can either talk about 5% or 2% settling time. That's basically the time it takes to get within a certain percentage of the steady state. Okay. So if it's within a certain percentage, so it can be 5% or 2%, depending on how stringent you want to be. Okay, so this is the settling time. So that's TS. Okay, settling time. And there's a formula for that. All right, so that's how long it takes for the trajectory, right, to come within 5% or 2% of the final steady state. Another one that's used is how long it takes to get from time 0 to the first peak. Okay, so that's the peak time. So that's TP, unsurprisingly. Okay, and there's a formula for that. So that's another one. So you can imagine if the oscillation is more violent, the peak time will probably be smaller. Then the last one is the maximum overshoot. So you'll notice that these oscillations, they sort of diminish. Well, that one should be smaller than this one. That one definitely diminishes. The overshoot and the undershoot get smaller as time goes forward, and there's one quantity which is the first peak, the first overshoot, and that's called the well, it's actually of the percentage. It's the percentage overshoot. It's got different symbols, but MP is a common one. Okay, so these are the various metrics you can have for looking at the performance of the second order system. The one complication is the rise time, which is different depending on whether your zeta is greater than 1 or zeta is less than 1. If zeta is greater than 1, it's just like the first order one, which is the time it takes to go from 10% to 90% of the steady state, right? You can't go to 100% because it asymptotically approaches the steady state, so we can't talk about that, but we can talk about when it reaches 90% of the steady state. If the dampening factor is less than 1, then you'll have a damped oscillation, then you can't really talk about, you can talk about 10 to 90%, but it's not that convenient. So instead, they talk about how long it takes for the line to cross the steady state, first time it crosses the steady state. Then the other ones which are unique to the then the other one that's common to the first order system is the settling time. Okay, how long it takes to come within a certain percentage, and the other two are unique to the second order system, which is percentage overshoot and the peak time. Okay, and I said it was going to be short, and it was short. Okay.